Please, I hope you can see my screen. Please, can you see my screen?
Yes, yes, we can see.
Okay.
Yes, we
Good afternoon,
can.
everyone. I am Tata Herbert by
Yes,
name.
we can. Go on, go on.
Yes, Tata Herbert by name. I'm presenting this paper on the title Assessment of Positional Accuracy on the Global Navigational Satellite System, which is GNSS. And first and foremost, we have to know what GNSS is all about, which GNSS stands for the Global Navigational Satellite System, and it is a standard generic name for satellite navigation. And the system provides autonomous geospatial positioning with a global coverage, which is mainly based for the GPS, the GLONASS, the Galileo, and the BIDO. And it also refers to a constellation of satellites providing signals in space. That is the GNSS. And this GNSS, as we said, that is a generic name, which combine of the GPS, the GLONASS, the Galileo, and the BIDO. And then the GPS is owned by the American, while the GLONASS by the Russians, then the Galileo by the Europeans, and then the BIDO by the Chinese. In fact, the essence of this work, why we are doing this, because most of the GNS stations that are being established, especially if they want to bring it down to Nigeria to establish them, because part of the stations are used are the stations in Africa, which stations are being linked to international terrestrial reference frame. They are like base stations, where if we want to establish our own stations in Nigeria, we can use these stations as the base for it. So there's a need for us to know if these stations are still institute, whether these stations are still okay or they have been tampered with. So there's a need for us to know whether if they are okay, then we can always use these stations. Now, this GNSS, it provides real-time navigation for us, especially in position, for velocity, acceleration, direction, time, and then it means of titration with navigational satellite system. And some of these applications that we use this GNSS for, like in surveying and mapping, we can use it for transportation, in mining, seismology, meteorology, precision farming, port automation, marine defense, and so on and so forth. So most people use it. Even our handset, we have it. It's being installed in our handset. And there are some handsets you have the GPS there, and you have the GLONASS, and you have Galileo. Even some of the, like when you use all this, you can use it to navigate. You go to places, they help you in going to so many places. Now, the next slide. Now, we cannot talk about this GNSS without talking about the segment. It has 3 segments, which are very much important. That's the space segment, then the control segment, and the user segment. Now, this space segment talks about the constellation of all these satellites that we are talking, the GPS, the GLONASS, the Galileo, and the BIDO. And of all these, GPS is the most widely utilized system. It's a widely utilized system. Now, when we talk about a control system, control segment, we talk about the data uploading and downloading. That's when you use your handset, you can download it. You use your GPS, we call it different type of GPS. We have our differential GPS, we have handheld GPS, and so on and so forth. Some of the GPS are being installed in our vehicles, which comes about to be user segment, where you can use it to drive. Our aeroplanes use it, you can use it for navigation. Our GPS use it to map our positions, where the last speaker just talked about capturing data. We use the GPS, the handheld GPS, to capture all this data. It helps a lot in capturing this data because of the accuracy. It has a good accuracy, especially when we talk about we'll talk about the advanced GPSs, like dual frequency GPS. They have a very good accuracy that we can use, especially the core station, that is continuous operating reference system. It works on order 0. And one of the reasons that we need all these things, because it helps us in monitoring things like earthquake, things like tsunami, things like, take for instance, what happened in Nigeria in Kwe when they are talking about the earth trauma. All these things, once if we have this data and we're able to capture this data and use it, we can monitor all these things to see that, okay, there's a shift. The data, there's a shift here. This is the level of the shift. It's going to happen this. So you're able to dictate if the changes can be either horizontal or a vertical movement. Now, one of these stations, as we're talking of this GNS network, is the CORS, which is a continuous operating reference station. And this continuous operating reference station, it's a permanent, always on a permanent monument, stable monument that have steady supply of light and internet connection for continuous observation and stream of GNS data. But we have a challenge that do we really have it effective in Nigeria that will continue streaming this data? Now, on the screen, you look at it, you see a sample of that the core station where you have the antenna, you have the solar panel, you have the charger, the router, the receiver, and the battery. Now, this thing is supposed to be streaming data, but there's a level of data that you need to access. Now, if the stations that are installed, if they are institute, and the stations are really functioning well, then it will solve a lot of problems that we have. Like, we solve a lot of problems that we are facing in times of shift, in times of deformation monitoring, and so on and so forth like that. Now, the introduction of this technology to African countries is a right step that we need to pursue, because most of the developed countries have introduced, like in Nigeria, we have about 11 of these stations that is being controlled by Office of the Secretary General of the Federation. Like in UNN, where they have it, they have one of the stations there, which is one of the best stations or required stations that we always have our data from. Now, in recognition, hello? Yes, can you hear me? Okay. Now, in recognition of this strategy, the important navigation, it is potential and the need for us, for the African states, to join the other African countries to benefit from it. But before we join other African states to benefit from it, then we have to know that these very stations that we want to tap from, that we want to take our base from, which are being linked to ITRF, that is International Terrestrial Reference Frame, which has been linked to, are they institute? Have they been tampered with? Because if they have been tampered with and we use them as our control and our base, we will have issues. We'll be having wrong information. We'll be having wrong signal. So that's the need that this research is carrying out, to see that all these things are instituted. Now, this is the methodology flow chart. First and foremost, there was data acquisition. And two types of data were acquired. We have the RINEX data and then the ephemeris data. And then this RINEX data, RINEX stands for Receivers Independent Exchange. Now, this RINEX data is globally accepted. And then the data, once it's coming, you need to convert this data into observational data, because the data are so many. So the data we are converted into observational data that it will help us to process. And then these ephemeris data, too, when they come in, they are always in zip format. So it had to unzip it. We have to unzip it. And then there's a program that we need to convert. We call it Hatanaka program, that we have to convert this RNA data into. Once these data are converted, then you import them into your software. You import them into your software. And the software that was used in processing data, we call it TTC, that is Trimble Total Control, which is a scientific software. And before you process it, there are a lot of settings, parameters that you need to set. You need to set the baseline, you need to set the network adjustment, the baseline. You have to process the baseline, because now there's a particular, because when you are processing, it needs a particular carrier phase that you need to use. Like we have the L1, that's the band, the L1, and then the L2 frequency. But for this software, we need to use LC. This is ionospheric free error, because the software requires that the distance between each of the station and another station shouldn't exceed 500 meters. But if you look at it in our country today, we are just having 11 or so within the country. You have one in Futa here, you have one in Enugu, you have one in Lagos. There are more, the distances are so wide. So it means that it can incur a lot of errors. So once you set them at ionospheric free, it carried out all these corrections. It corrects the error, especially like cycle sleep. There's an error we call cycle sleep. The cycle sleep is sudden jump in processing. In when you are downloading your value, a sudden jump. A jump is skipped. Is like a gap between one satellite and the other. At that particular point in time, there won't be satellite at that space, but it's keep on streaming data. So you need to process to remove out all these errors, so that you can get a better result. Now, setting of the processing parameters which we carry out, then you process your baseline. Why are you processing your baseline? You process each individual baseline to see if this baseline two are okay. Then you adjust your network to see if there will be a closed network. To see where they will. Then, after adjusting your network, the next thing you do is you now do what? We carry out our data analysis, then coordinate dispersion. Now, because of the limit of time, they say we can use only 6 slides. I just bring out the baseline, the result for the baseline residual. Now, if you look at this result now, you will now notice that the result from 2016, 2017, and 2018. Now, this thing was carried out, the trial was carried out within this period, and it was because of the availability of the data we were using. Now, these are the stations. We have the Hubs to Mbarara or MBA, and then Hubs to NKLG, Hubs to RB, and Hubs to Simon. Now, if you look at this, from if I was to present, I would have shown you the distances, which is in kilometers, between one station to another station. Now, from these hubs to RB, it has about 500 and something kilometers. That is why you discover that the values are different, a bit lower than all other ones. So it means that if we have more of these stations around, we'll always be having better result. So if the distances are far from each other, it will always affect the result we are having. So there's an encouragement that we should have more of these stations, so that we will have more accuracy in what we are doing. Now, in conclusion, the study attempts to carry out assessment of the positional accuracy on the global navigational satellite stations. And then in this study, the analysis were based on coordinate dispersion and then baseline residuals. And then further analysis was carried out to compare the given coordinate and then the stations that we have processed. Because initially before we carry out this, we have the coordinate in which those stations were being installed. So when we process, we now compare the two to see if there's a discrepancy between the two coordinates. And the analysis of the result reveals that the stations are still institute. Nothing has been tampered with. And as such, these stations can still be used for surveying and mapping and any other work we want to use. So these stations can be used in establishing other stations. We can use these stations to coordinate or to coordinate the other network that we want to coordinate within the country and within our state. Thank you for listening. Thank you for listening, sir.